Be strong.
No.
Be strong.
No.
Right? Oh, sorry. You have the title? Resistance. Yes? Yeah. Okay. Yeah, so maybe it's good to start this by giving some definitions which you need. Current, which we were talking about in the last class, is the rate of change of change. No, that's a typo. That's to say charge. Please change the second word to charge. Rate of change of charge. Not change of change. Change of charge. Oops, sorry. Well, I can change it here now. It should say change of charge. Okay, so you need to fix that. Right, that's current. Charge you've already done a little bit in chemistry. So electrons have negative charge and protons have positive charge. And we talked about this yesterday. So this is it as a formula as well. Current is the charge divided by the time. Yep. Yes? Okay. Voltage. Now this is new. Voltage is how much potential energy there is per unit charge. And the unit is joules per coulomb. You know what? I've actually decided that question I was doing, which I said to be continued, it's been cancelled. Yeah. I like doing difficult questions, but Carrara reminds me of the fact that it's not actually on the exam, so we'll just cancel it then.
You like, we don't like.
Exactly. So I need to sometimes remember this. Okay. I'll just go to a little picture here I want to draw for you. So what I'm saying with voltage is when you have something like an electron has negative charge. When the electron moves from here to here, we call this a current. We call it a current when a charge moves from A to B. When this charge moves, it could do some work. For example, it could light a light bulb. So you know, like the lights here, is because there's electricity going through it. Whenever a charge moves, it could do some work. So if this one, let's say here we had, for example, 1 coulomb, and if this 1 coulomb could do 1 joule of work, then we say the voltage is 1 joule per coulomb. That's what I'm saying here. That voltage is like how much work the charge can do. It's like how much work the electron could do. So the unit is joules per coulomb. So 1 joule per coulomb means 1 coulomb could do 1 joule of work. Another unit though is the volt. And 1 volt is 1 joule per 1 coulomb. The same thing. Got it? No? Yes? The next thing is resistance. So you might know this word in English. Resistance means almost like difficulty, opposition. So resistance of a conductor is a measure of the difficulty for current to move through it. So for example, something like something made of metal has low resistance. It is easy for a current to move through it. Maybe you've done conductors in chemistry actually. Have you done this? No, not yet. Conductors in chemistry? With Lorraine? No. So, metal, the resistance is low. The current can easily go through it. What would be something like wood? Does anybody know? Easy or difficult for a current? Difficult. So the resistance is high. Here, resistance is low. The current is easy to go through. Yeah. So you want your resistance to be small for the current to easily go through. Yes? Current to travel, yeah. Now, the unit we use for resistance is called the ohm. And what an ohm means that when there's 1 ohm of resistance, it means 1 volt of energy was converted into another form of energy per 1 amp. So just before you write that down, let me show you here what that means. What I'm saying is, if the resistance equals 1 ohm, that means that when 1 amp goes through and the voltage is 1 volt, what's happened is 1 joule, 1 joule of energy was produced, usually in the form of heat, but it could also be light or sound. So when 1 amp travels through 1 ohm of resistance at 1 voltage, then it means 1 joule of energy was made, of work was done, usually heat. So for example, the resistance here is very big. So if I put a current through the wood, it should start to smoke, it should start to burn. Because the resistance is big, means lots of energy is converted. Okay. What if I put a current through some metal? Does it get warm? Not really, it depends on the metal. So if the resistance is high, it means a lot of work is being done. A lot of energy is being lost, usually. Okay, yeah. So you can write the definition down here. When 1 ohm of resistance means 1 volt of electrical energy was converted into another form of energy. Sorry, so just remember, 1 volt, what's the unit for volts? It's also joules per coulomb. So it might be helpful to write this as 1 ohm means 1 joule per coulomb of electrical energy was converted into another form of energy when 1 amp was passed through the resistor. And 1 amp, remember, is 1 coulomb per second. So it may be helpful if you replace voltage with joules per coulomb and amps with coulombs per second. It doesn't matter. You can write it exactly like this, whatever helps you understand it. Did you write this definition down? These are exam definitions. So for example, if there were 2 ohms of resistance, it would mean 2 joules per coulomb per volt, basically, of energy is produced by the resistor, usually in the form of heat. Not always heat, though. Most of the examples we look at will be heat, sometimes light. Can I go on? Not yet? Did you write all of this down? Yeah? I believe you. What's your question? Oh, well, we'll leave it then, because I'm going to continue. Can I continue?
Yes.
No! What's taking so long? Language, I see. I think I must continue now. Yes. So, just to be clear, really, these 3, current, voltage, and resistance, we use it a lot in this chapter. Like, they're the most common terms to see in this whole chapter. So it's important to picture the relationship between current, voltage, and resistance, okay? So the following picture will help explain the relationship between voltage, current, and resistance. Here's my picture.
Oh my God.
Let me explain. I think it'll make it clear. So look, the resistance tries to make it difficult for the current to move through. Yes? And the voltage is what gives the current energy to push it. So for example, if the voltage is very small, he cannot do much work because he's not pushing him. If the resistance is very big, then is it easier or more difficult for the current? More difficult. You can take a picture there. I know the picture is silly, but it shows you the relationship between the 3 of them. Yes? So, let's see. If the current, think about it like this. If the resistance is very big, did the current do a lot of work or a little work? No, a lot. Because he had to do, look how tired he is. He had to do a lot of work to pass through.
But he cannot exist if there is a lot of...
Now let's imagine that he squeezed through. If this is really big, does he need to do a lot of work or a little work? He must do a lot of work, okay? So with lots of resistance, that means there's lots of work being done. Okay? So for example, that could mean maybe that the voltage is very big. Or the current is very big. Anyway, the 3 always go together. Yeah? Okay. I hope this helps. Now, since we're talking about voltage, current, and resistance, we need a way to measure them. So we measure voltage by using a voltmeter. So please write the name down. We measure voltage by using a voltmeter. So, next, yes? Next, we'll do current. So next, how do we measure current? We measure current using, ammeter. So this is how we measure current, using an ammeter. For what?
Was like the meter and the taxi.
Yeah, altimeter, yeah.
Meter.
Yeah, yeah. Because meter means like something that makes a measurement.
Yeah.
Yeah. And lastly, we measure resistance by using an ohm meter. Yeah. Measuring an ohm meter. Now, in fact, we never really use these because they're so inaccurate. So we don't actually use them in class. They're not very accurate. The ohm meter is inaccurate, yeah. Yep. Okay. Can I go on? No?
Are you sure?
They all look the same. I mean, if you look at the picture, they all look the same. V, A, ohms.
These are the old versions.
Oh yeah, these look the nicest for pictures. Yeah.
Oh yeah, these that we have like.
Oh no, this is the ones we'll use. Yeah, I'm saying these look the nicest. Okay. First point. Listen, you don't need to write this down. These are just some points to note. We will not use an ohm meter. They're too inaccurate. Okay, so we don't actually use an ohm meter. We will use voltage and voltmeters, and we will use current and ammeters, but we won't use ohm meters. And these two notes are best explained with a picture. So, if I have a current, I, and I want to measure how much current I have, I use an ammeter, and I put the ammeter in the middle of the current. So then the ammeter, I can read the current from the ammeter, like this. So, in other words, if I go back to my picture maybe here, you can't quite see it here, but you put one cable in the black and then one in the red.
Yeah.
In this particular one, there's 3 different settings for low, medium and high current. So if you have a high current, you can put one here and one here. So the current goes in one side and out the other side. If you want to measure voltage, it's quite different actually. If you want to measure the voltage, you put the voltmeter, you connect it around, like this. And what this will tell you is it will tell you the voltage from here to here. So you never, so this is quite bad, don't ever do this. Voltmeters don't work like this. Voltmeters must be connected like this. And yeah, in parallel. Yeah. So this is right, and this is very wrong. So voltmeters don't work like this. They're always connected as so. Now, in this example here, I know that this here will say 0 volts. And the reason for that is you can only measure the voltage if something was being used. So for example, if I put a light bulb here, then I can measure some voltage, like 10 volts. But if this is empty, then this will be 0. So in other words, voltmeters only make sense if you put them around something that's using energy. So you can only use voltmeters when there's some energy being used. Like, example, a light bulb. There must be some resistance. Don't worry, I will show you how to use these machines in class, okay? Yeah, we'll have practicals on them, okay? So let me show you on a diagram. I just showed you on a diagram. Right, so we have some questions. Although I forgot to give you write the formula down. So the last thing to do is the formula for resistance. So there's two ways to think about it. V, I, and R. You can draw it as a triangle. Sorry. So you can have these formulas that relate V, I, and R. V is equal to I, R. Or you could say R is V over I. Or I is V over R. So you can use this triangle to help remember that. What triangle does this remind you of?
The
Distance, speed, and time. It's like distance, speed, and time. Now, please also remember, what's the unit for voltage? What did I say 1 volt equals? 1 joule per coulomb, okay? So this part here is like work. So for example, if the voltage is very big, was there a lot of work done? Yes. Now, do you remember the picture of the push-it? Yeah? If the resistance is big and the current is big, if the current is strong and the resistance is strong, was there a lot of work? Yes. So the V is like work. What I mean is, if the V is big, it means a lot of work was done. A lot of joules per coulomb was converted. Okay. So these are the three formulas: 1, 2, and 3, and they all come from this triangle. You got that triangle? Let's have a look at some questions now. Right, so write this one down. So let me make a note here. Fill in this, and I need to add in my triangle. No, not killing this. Killing this. Oh. Milliamps. Okay. Can I do it now? No? Light bulb. Yep.
like you.
Huh?
That's not about that.
True. Close enough. You got it? Yes? Yes? Okay. So let's have a look at this one here. So what's happening? You have your light bulb, and I put a voltmeter here. Did I say a voltmeter? Yeah, I said a voltmeter. And what did I say the voltage was? 220 volts. And then I put an ammeter here. Oops. And what do I say the current is? 250 milliamps. So I would like to know what is the resistance here. Well, what formula can I use? R equals V over I. That would be 220 over 0.250, which will be what? 880 ohms. So resistance, in fact, is quite large here, quite large. Huh? Question? Grace? Question? Yeah. So what happened here is this here is milli. So this is 10 to the minus 3 milli. Let me remind you. Centi, 10 to the minus 2. Milli, 10 to the minus 3. Kilo, 10 to the 3. Do you remember this? Yeah. So if I have milliamps, like millimeters, it's like 10 to the minus 3 for milli. No? Or yes? Yes? What are these called, Grace? What are these called? You're not Grace. You wish you were Grace. You're not Grace. Yes. Prefixes. Yep. You remember this word? No. Okay. Some people do. Okay. What's this? There's nothing there. You know this one. And you know this one, and you know this one. And do you remember this one, Amanda? Amanda. Micro. And nano. Yeah. And mega. Mega. 6. Yes? Huh? No, we're finished now in a minute. I don't know if there's another question. Let's see. Yeah, one more question. Okay. So look, we'll just draw this one instead. So you have a 6-volt battery is used to power a toy of resistance 2 ohms. So let me draw that one. So you have, I don't know, 6-volt battery. I'll draw it for you. And the current comes out into some toy. I don't know. Let's say PSP or something, or Game Boy. Everybody remembers Game Boy. Yeah. Okay. And I tell you here, the resistance in the Game Boy is 2 ohms. And my question is, what is the current? So I know the voltage, because it's on the battery. What's the voltage? 6. And I know the R. So which formula should I use to get the I? I equals
V over R.
V over R. So that would be 6 over 2, which is 3. The I is 3. Okay, that's the first part. Is that okay?
Yes.
If the toy is left on for 1 minute, how many electrons flow into the toy? So what's happening here is there's electrons going into the toy, and it's left on for 1 minute. So we need to use the formula from yesterday. Q equals IT. What's the I? 3. And what's the T? This is part 2, this is part 1. 60. I said 1 minute, didn't I? Yeah. So that's 180 coulombs. So the number of electrons would be 180 coulombs divided by the charge of 1 electron. What was that? 1.6 times 10 to the minus 19. So how big is that? Please, can you type it in? There'll be a lot of electrons flowing through in 1 minute. What is it?
1.125 times
10 to the power 22?
21.
That's how many electrons flow through it in a minute. Okay? Next is Aya. So, in the last part of the question, I replaced the battery with a 6 volt, I replaced it with a 12 volt. So my question then is, what is the current now? So, think about this. Like, can we look up, listen? So, instead of having a 6 volt battery, I have a 12 volt battery. Can a 12 volt battery do more or less work? More work. Now the Game Boy is the same, so the resistance is the same. So if the resistance is the same, but the voltage is bigger, do I need more or less current? No, less.
Yes.
Okay? So remember the volt in the picture, remember the voltage is like pushing. Okay? If the voltage is stronger, if the voltage is bigger, then does the current need to be stronger? No. The current can be smaller because there's more voltage pushing. Yeah? So like I don't know what other example is like this. All I can say is if there's more voltage, then the current can be smaller because the voltage is stronger, it's bigger. Anyway, what is the formula for voltage? What's the formula? What is it? V equals IR. Yeah? What's the I? Oh, sorry, I don't want the voltage. I mean, what's the formula for current? I equals V over R. What's the V here? 12. And what's the R? 2. So what's the current? Oh, sorry. I'm hungry. It's lunchtime. So sorry. The current is bigger. I said smaller, didn't I?
Yeah.
That's totally wrong. It needs to be bigger. Yes, I said it backwards. If the voltage is bigger, never mind. The current is bigger. Let me, hang on, let me go back to my picture. Yeah, here we go. Alright, hang on. Alright. This is the same. This is the same and this is bigger.
You can push it more harder so it will.
Yeah, so this can be bigger. Yes. Yes. If this is the same and he is stronger, then this must be bigger.
Output will be bigger.
Ah, okay. So if he's stronger, this can be fatter. Yeah. Maybe it's easier to think about it this way. So if this is the same and he is stronger, then he can be fatter because he is stronger. So this should be bigger. Okay, does that make sense? Yeah. What did we say the formula was for I? V over R. So that will be 12 over 2, which in this case is 6 amps. Wait, I just put these up. Wait. So what I want you to do is, if you want to take a picture of this, you can. You need to take out your laptop for the test. The test is available at 12 o'clock, which is now 1 minute ago. So you have to do it on Moodle. Oh, and good news, I'll give you the formula book.